The subject of today's lecture is stem field, splitting field, and algebraic closure. So consider a polynomial p in k of x, which is irreducible and monic. Let me give the definition. A stem field for p is an extension E such that E contains a root of p and is generated by this root. Well, such a thing exists. We can take just k of x modulo p. This is a field since p is irreducible. Well, on the other hand, any stem field E is isomorphic to such a thing. Well, it is easier to define the isomorphism in the other direction. Well, let's say kx modulo p goes to E by the following formula. So f goes to f of alpha. Okay? To summarize, we have the following proposition. So a stem field exists and if E and E prime are two stem fields for p generated by roots alpha and alpha prime, where alpha and alpha prime are roots of p, then there exists a unique isomorphism from E to E prime, taking alpha to alpha prime. Well, this is, of course, easy. So existence we have already seen. Uniqueness of the isomorphism. Is easy since an isomorphism of k of a alpha with something else, with any field, well, let's say with E prime, is defined by the value it takes on alpha. Well, of course, I have to be precise here. I said there exists an isomorphism, but I must be precise and to say an isomorphism of what? Of course, not only of abstract fields, but of extensions of K, so of K algebras. Then it is really defined by its value on alpha. So what I have to prove still is the existence of such an isomorphism. But this is easy because I have phi from k of x mod p to E. I have psi from k of x mod p to E prime. And I just take psi minus 1 times phi. this will be an isomorphism between E and E prime. And of course, it will take alpha to alpha prime. So here it takes x to alpha. Here it takes x to alpha prime. So my composition will take alpha to alpha prime. Okay. So in particular, remark. In particular, if a stem field contains two roots of P, there exists a unique automorphism of it taking one to the other. Well, first of all, secondly, if E is a stem field of an irreducible polynomial, then of course the degree of E over K is the degree of P, and conversely, if the degree of E over K is the degree of P and E contains a root of P, then E is a stem field. Otherwise, its degree would be strictly greater than the degree of P. Well, now I can give you some more irreducibility criteria. Corollary 1. So if P is irreducible over K, rather P is irreducible over K if and only if it does not have roots in extensions L of K of degree less or equal than n over 2, where n is the degree of P. Well, how to prove such a thing? It's very easy. Well, proof. Otherwise, if P is not irreducible, then it has a factor, a prime factor, irreducible factor, Q of degree less or equal than n over 2, and one can take its stem field as L. Well, in the other direction, conversely, if P has a root alpha in L, then of course the minimal polynomial of alpha over K divides P. So P cannot be irreducible. Okay. One more irreducibility criterion. Let P be a polynomial over K, which is irreducible of degree n. And let L be an extension of degree m. If n and m are relatively prime, then P is irreducible over L. Okay, you see, so an irreducible polynomial might become reducible over an extension, but it does not happen if the degrees are relatively prime. Well, proof. If this is not the case, Q divides P in L of x, let M be a stem field of Q over L. So we have K in L in M. Well, M is L of alpha. So K of alpha. Well, alpha is a root of Q, so it's a root of P. Is a stem field of P over K. So its degree over K is equal to n, the degree of P. Well, on the other hand, if the degree of Q is G, then G is the degree of M over L, because M is a stem field of Q over L. And so the total degree, the degree of M over K, is M times D, because it's the degree of L over K times the degree of M over L. But K of alpha is a subextension of M. So the degree n must divide md. And so, since n and m are relatively prime, then n divides d. But d is less than n, so n is equal to d and p is irreducible over L.